Paul for having me here. I'm a sort of odd one out. I'm not an oncologist. I work in this field now more or less by chance. And well, I'll share the screen and wow, I have so many windows open that I have to find the right screen to share. My God. Where's Acrobat? Where's my Acrobat?
So you see the little like green button of sharing screen?
No, yeah, I have, but I have so many screens here in the sharing thing that I just can't find the one that I should be.
Okay.
Where is it? Ah, this is the Acrobat that I don't have my talk, but I have something else. Okay, now this is it. So I'm sharing the schedule. Now I'm sharing my screen. Okay, so you're seeing the end of my talk. Okay.
Exactly. I'm reconstructing the hidden chain right now.
Okay. So are there any questions? Okay, so are we on schedule? Yes, we are. Okay, so well, as I said before, thank you, Paul, for having me here, and for the ones that are listening, thank you for your patience. And okay, I'm gonna talk about something which we have done some time ago, and when the COVID began, well, February, March, early March this year, we were having coffee with one of my colleagues, and we were looking at the data on COVID, and we said, well, but we have a model for this. Let's see where we can get. And well, we began to work with our old model and had to change some things because we needed different stuff. And that's what I'm going to tell you, what we have done with our old model updated to our present pandemia. So introduction, what's under reporting, how does the model look like, applications, and things to be done. Okay, so under reporting is, as the word says, some phenomenon responsible for reporting less counts.
I'm sorry to interrupt you, but I still see the last slides of your talk. I don't know if it's the same for everybody.
Really?
Yeah.
Oh.
I thought you would change when you would do the.
No, yes, I am changing them. Well, let me share again the screen.
Right.
Wow. What's wrong? Okay, so here it is. I'm gonna close everything.
Now I'm good, I think. The number of infections, but yeah, now it changes. So I think if you go at the beginning, then it will be good.
Okay, so the beginning was just me.
Yeah, that's good.
Who should be in Paris, but I'm in Barcelona. Okay. I said briefly the overview of what I'm going to say, and then begin about talking about underreporting of data. I guess most phenomena are underreported. I mean, you usually have less information available than the one there is, especially in situations like the pandemic, illnesses. There are a lot of ill people that don't show up in the official registries. So we miss them. In this case, in the case of COVID, mostly because of asymptomatic individuals that never get to be tested, or people who have few symptoms and don't even go to the doctor. At the beginning of this, February, March, when we began to work on this, the principal problem, at least here in Spain, was the lack of tests. So there were people that were not tested, and doctors knew that they were ill, but they didn't show up in the registries because they were not PCR positive. There are several reasons for which the number of counts are less than the ones that there exist. So, and this is reported in the press, undercounted, whatever. So, in 2016, an old paper in Statistics in Medicine, we had a very simple model for working with underreporting in different illnesses, more simple ones, perhaps. And the model worked in the sense that, well, we did a lot of simulations, and in simulations, we could recover the percentage of, I mean, we simulated data from our model and then underreported them, reported less than what the simulation said, according to the mechanism we have devised, of course. And well, the estimation procedure could reconstruct fairly well the simulation scenarios. And also we had the data on different underreported situations, genital warts, papilloma virus and such. And the results we got about the percentage of underreporting coincided with the idea that the epidemiologists had by that time. So in this sense, we were happy with the results. And well, it works. This was devised for stationary series, but we also made some changes for non-stationary series, seasonal or with trends, which is the case of the data we have now, and with covariates. And this worked well in that time, so we said, okay, let's try to use it here. So the model is very, very naive, but it works. It's, imagine that we have a hidden process, xn, with Poisson in R1 structure that is an autoregressive. In R is an integer autoregressive process of order 1. In order to have an integer autoregressive process, what we have is binomial thinning of the number of counts we have in the previous step, plus a noise. This noise in this case is Poisson, but it could be something different, negative binomial for over dispersion. But in this COVID case, it seems that Poisson works okay. So we didn't try to fit the negative binomial because it seems that it's not over dispersed. Okay, so what we have is a binomial thinning of the previous step plus our Poisson noise. This is a very, very simple model. It's an homogeneous Markov chain with transition probabilities which are very easy to derive. And of course, this lambda immediately will change to be time dependent. So we will not have an homogeneous Markov chain. We will have a series with a random environment, like the ones that Paul, Newman, and Truquet work with. But it's very, very computations, I mean, theoretical computations for these things are quite straightforward. Okay, and then how do we underreport? Again, very naively, saying that at each instant, n, what we see is either the true number of counts with probability 1 minus omega, or a binomial thinning again with probability omega. And now, well, omega will be the frequency of the underreporting, and q, the overall, the intensity of the underreporting process. This process will be IID. But again, then q can change with time, so we will later on develop things to allow q to be time dependent. So what we see is a mixture. Either we see x, the true process, or we see less than x, a binomial thinning. So again, this way of writing things allows for computations of everything about the distribution. So the stationary distribution of this, the original, the latent process, will be a Poisson with a damped mean, and the autocovariance and autocorrelations correspond to an autoregressive process of order 1, so they decay exponentially. And the observed process, in turn, happens to be, I mean, the autocovariance function of the observed process will be roughly as an autoregressive process of order 1, with exponential in k, exponentially decaying, but damped with a constant that doesn't depend on the lag. It depends on all the other parameters, but not on the lag k. Okay, so we have to estimate the parameters. The parameters of these models are, well, alpha, lambda, q, and omega. So the estimation is done based on maximum likelihood. And the likelihood is ugly because it's not directly tractable. It's a hidden Markov model with transition probabilities given by the transitions of the original Markov chain, and the emission probabilities, the probability that if you see what you see, given that the truth is x, then what you have is, well, it's very simple again, the sort of emission probabilities, they come from the mixture that we observe. And then, since the likelihood is ugly, it can be computed recursively using a forward algorithm. Forward algorithm is quite old, but it's quite fast. Just by defining forward probabilities of the chain. So we have that the likelihood is a sum of these forward probabilities that can be computed just by multiplying a matrix by a vector. So this thing works. The problem with this is that if the number of possible states of the original, of the hidden layer, is very large, then we have numerical issues for computing this. But apart from that, from the theoretical point of view, this is quite straightforward. So we have parameters estimated by maximum likelihood, and then we have to reconstruct the hidden chain. And the reconstruction of the hidden chain, again, is something widely known with the Viterbi algorithm, is again maximizing the likelihood of, given the observed series, and assuming that the parameters are the estimated parameters, then what we choose is the chain that maximizes the joint probability of the x and the y's. So again, this Viterbi algorithm is very, very computationally fast, so no problem with this, even for large number of states. So we have everything. We have things estimated. The problem is that what we were talking about before is for stationary series. And then when we want to use it here in our case, these are coronavirus, the number of daily PCR positive cases in Spain. This was at the beginning of the pandemic. These data are up to May 24. As you can see, these data are far from being stationary and far from being clean. We have this negative number of counts here. This is a disaster. I mean, data from this pandemic are dirty all over the world, except perhaps for Swiss. And Swiss data are quite clean, but all the other data we have seen are terribly messy, dirty. They record them badly. One day they give you PCR positive cases, and the other day they give you all possible tests positive. We have to deal with terrible things. I live in Barcelona, so I'm especially interested in what happens here. And these green lines are Catalonia's cases, our region, and we had here a higher peak than in the highest moment of the pandemic, which is absurd. These data are spurious. But we work with this data like they are, even with, well, no, we cut off the negative counts, of course. But beside that, okay, well, the point is that the data are far from being stationary, so we had to do something. Okay, so the first thing we did was say, okay, the mean of the latent process is time varying. And the other thing that we saw is that the intensity of the underreporting is also time varying. And this is especially interesting because there are periodic effects in the observed series. And it's absurd to think that the true rate of contagions is periodic. What is periodic is the way that public agencies produce the data. For instance, we were working with positive PCR tests. Okay, so an epidemiologist told us that people mostly go to the doctor on Mondays, and PCR tests take 2-3 days to give the result. So we had very high peaks on Wednesdays, and systematically we had peaks on Wednesdays here in Catalonia. And well, if you studied those data, I mean, people don't die on weekends and things like that. So the periodic effect on the series, of course, is not due to the original process, to the latent process, but to the observed process. And this, we can reflect it by allowing to have periodic effects here on the frequency of underreporting. Okay, but how do we model the mean of the latent process, which is more interesting, because if you look at the mean, well, the mean here changes. I mean, it goes up and then goes down. So that has to be reflected in the mean of the process. So what we did was consider the simplest SEER model for modeling epidemics, where we have healthy but susceptible individuals, infected individuals, which are the eyes, and the people removed from the system, either because they are recovered and will not get infected again, hopefully in the case of COVID, though yet we don't know. And now I guess that they are finding that people removed can also get in. So this might have to be extended somehow. Well, but anyway, what we did was use a simple SEER model. Well, here in the removed, we have the recovered and the dead as well. Okay, and the parameters of interest here are beta and gamma, the rate of infection and the removal rate, and the susceptible population. Okay, so we consider this model, but now we simplify it. We consider only the affected people, and the affected people are the sum of the infected plus the recovered. So we sum up the two first equations and replacing the infected by what they are, then we get a simpler system of differential equations. We got rid of one of the equations. And with this simplified system of equations, we can find an equation for the variation of the removed with respect to the affected. And we have the solution, but this is a separable variable equation, so we have the exact solution for that. And replacing this here in this first equation, we get a nice equation for the population affected by the disease, and with a Taylor expansion of order 2, we have a really straightforward solution for the number of affected people. The equation for the affected people has a logistic solution, changing parameters. So what we have is a very nice form or approximated form of the solution of the SEER equation. Okay, and now we consider as the mean of the latent process the newly affected individuals in time n. So the mean, the expectation of the hidden process of time n will be the difference between an and an minus 1. So what we have is an exponential growth at the beginning and then an exponential decrease, which roughly seems to be what's going on with the graphics I showed you before. So now the parameters of the model are alpha and well, the m that comes from the solution of the logistic, which has to deal with the number of individuals. We will call it small m at the logarithm of this quantity. We have a k that comes also from the solution of the logistic. It's the exponential in the logistic here for the latent process, and we will have omega and q or qn in the underreporting. So we are adding up parameters here. We have 1, 2, 3, 4, 5 or more, because qn can have its own parameters. So we end up for some applications with up to 7 parameters, which are again used estimated by maximum likelihood, but likelihoods for 7 parameters can be messy. Even though the forward algorithm works, it can be slow, and there is a major issue about the original, the initial values. If you don't choose well the initial values, then you can end up quite messy. Okay, so we can estimate. Once we have the estimates, we can reconstruct the hidden chain, the latent process X with the Viterbi algorithm, and we would like to forecast. So we can forecast in 2 ways, either with the expected value of the observations. Expected value of the observations is quite straightforward. So, well, we can write it down. And the other thing we have is, we have the estimation of the yn plus k, say, and we via delta method. Delta method is a weird way statisticians use to call the Taylor series when you are computing the Taylor series with respect to the parameters. So with a Taylor series with respect to the parameters here, we can derive standard errors for the predictions. And the other way to predict is using the conditional distribution of the observed process. And the conditional distribution of the observed process is ugly. It's a mixture of two components. Please forgive me for the awful way of writing this. I know that this cannot be written like that. I never do this when I teach. But it's a mixture of two things that are sums of a binomial plus a Poisson, different binomials, different Poissons. So we can have the conditional distribution of the observations given the latent process, and we can have, of course, the confidence intervals as well. So we have forecasts, we have everything we want to have. And let me now, what's the time? Okay, I have time. In the 15 minutes I have left, let me show you some results of these. Okay, so these data are from Sevilla, a region in Spain, the province of Sevilla. Well, what we have is official data that can be downloaded from here. It's old data. I don't have things after summer because in summer I really needed vacation and I ceased making estimations. Okay, so what we have here is, well, we see that most of what happens one day remains the day after, and lambda is, this was in the middle of the pandemic. I mean, lockdown was here, was among these days. So what we see here is that the mean went up and then went down. I will show you examples where the mean of the observation process is quite different from this. But in the time where we were in lockdown, things really looked like this. Then all means had this peak and then a decrease due to the lockdown mostly. Okay, and the model of observations, we had variable Q. We didn't need in this case, well, we tried a periodic effect here, but we rejected the model. I mean, we compared the Q, this logit, and the Q with the logit plus seasonal terms with frequency 7 days a week. And the parameters for the seasonal component were not significant, so we removed them. So what we see is that the rate decreases. So that means that we have more over-reporting over time, getting stronger. And this is quite terrible because by that time we were only seeing 66% of the cases, that, assuming that our estimation of the true number of cases is true and not the observations, of course. Okay, this is how the thing looked like. The blue ones are the observed cases and the red ones are the estimated. If you see, well, I was going to say something about that, but can be said about any other things. Okay, we can do that for many other places. For instance, Uruguay, my home country. In Uruguay, things were, we had very low counts in Uruguay. There are 3 million people country, so the number of cases was low. But when a peak came, then these peaks in Uruguay were identified. Hospital, a mental asylum, where they found a lot of people ill the same day, and so on. This thing that the reconstruction is a sort of a convex hull of the original is quite disturbing, but it is what it is. Okay, again, cases in Catalonia, separated by gender. Why is that? Because we had many cases. You see here, the peak, this peak is 116,000. And well, we couldn't deal with all the numbers together, so we had to split in men and women. We also did by province, but with large counts, we do have problems, so we need more robust numeric methods. This is Barcelona immediately after the lockdown. The lockdown ended in June 22nd, and this is immediately what happened afterwards. So again, the blue line is the observations, and this is the reconstructions. Things were going up 15 days after the beginning of summer, where there are parties in the beaches with fireworks and stuff. And this seemed to have, okay, so bursting again. And what's nice here is that the form of lambda here is increasing. Well, I shouldn't say it's nice. From an epidemiological point of view, is terrible. But well, then it was growing. And here we had interesting seasonal behavior with the Q. And as for predictions, well, these are predictions based on the conditional distribution. The gray lines are the observations. The red lines are the 95% confidence interval. And the blue line is the mean of the conditional distribution. And the yellow line is the median of the conditional distribution. And well, except for a few cases, all the observations lie in the prediction. I mean, we predicted up to here, with data up to here. The other thing were just for testing. And well, so predictions are not that bad. I would say they're quite good, in fact. And well, so long for that. What else do we have? Okay, we can think of a more complicated structure for the model and consider it an ARMA PR with the Gaussian noise for the intensities or prevalence or stuff like that, and for large counts as well. And well, if you have an ARMA and again use this very simple underreporting mechanism, then the moments can also be computed, and they are again a horrible multiple that doesn't depend on the lag times the original auto correlation function. So in this sense, it's okay, and this allows for more interesting models because it also allows general ARMA processes. Likelihood is not easy to be computed, but it can be done. Series can be reconstructed. It will be a mixture of two distributions and can be reconstructed using an EM algorithm. The maximum likelihood can be computed by EM, and then the reconstruction is a byproduct of that. And we use that and it worked. This is a paper we sent. Well, we are in the middle of a revision process here. And well, that's so it. What else can we do? Okay, put on higher in ARMA models. We can have covariates not only in the mean of the process, but other type of covariates such as temperature, somehow something that measures how spread the population is in the zone we are looking, rurality index. Here they have records of how rural a place is. Talking to epidemiologists, in some moment of the pandemia, they said that they were interested in over-reporting. When again there were some lack of tests, doctors diagnosed by symptoms. And some of the epidemiologists we were talking to said that out of fear or out of cautious, doctors perhaps were attributing to SARS-2 virus, some conditions that were not really caused by SARS virus, but were other respiratory syndromes. So the issue of over-reporting is interesting. And well, that should be taken care of. We have a sort of idea of how to do that. It can be done, but we are still working on that. And another thing that could be done is putting a different way of underreporting. Instead of an IID underreporting, then a Markovian model for the underreporting. We have a paper, again in Statistics in Medicine from 2019, last year. It's an application to gender-based violence, where we used a two-state Markovian model for the underreporting process, that you observe the true process or not, and there were some transition. It's a two-state Markov chain. And the idea is that it's not that it's a more realistic way of underreporting stuff, but it allows for more complex autocovariances. If you allow to have a two-state Markov chain, then the autocovariance of the observations are more complex than just a multiple of an exponentially decaying autocorrelation. So that's it. And well, this is it. The paper is about to appear in PLOS ONE. They are complaining about the captions of the figures. We are correcting the captions of the figures, and hopefully the paper will be accepted. It's the only concern they have. And well, we have a web page where we report some of the stuff we do, more than what I told you. And this is us. And well, thank you.
Thank you, Alexandra. I don't see any questions in the chat. Does anyone has questions? I can start, but it's a very general question. I was just wondering what was your take on the other types of approaches that are not based on count data, but more on phylodynamics or virus phylogenies to, for example, like fit the SEER model? And what do you think? Do you have any idea, you know this, and do you have any idea of the performance of this type of approaches, or what is the most promising, or just very naive, just curious?
I don't know. I mean, there are so many models these days that I just don't know which work better, which is more useful. I mean, I guess all the models we have here for this epidemics are, I mean, they all contribute somehow to understanding what's going on. And I guess they are all useful. And I'm not really sure they can be compared, because they aim at different things. For instance, we are also working with a Bayesian model that has spatial relationships, that takes into account spatial relationships between the places where counts are taken, but it doesn't give you daily, but overall underreporting issues, for instance. There are people who are now casting. I mean, they take the counts and they say, okay, no, these counts don't correspond to these
So
data.
I was really talking about the models that are not based on or fitting on count data, but on viral phylogenies.
Oh, wow.
We have this really different type of model. I know there's a lot, but I know there's these two parallel approaches, and yeah, I don't have a good idea of whether it's if it's really useful to have these phylogenetics models based on viral phylogenies and what they bring to the field. Or
I guess yes. I guess everything is useful, but
yeah.
I have the feeling that we won't be able to know what's really useful until some time from now.
Mm-hmm.
I mean, we have everything so bursting in our hands that I don't know.
Okay, there's a question from L2K. Do you want to say it aloud, maybe? It's good to have it written in the chat, but if you can, like.
Okay, I can answer the question directly. So I think that graphically, a situation that is shown for the prediction of the number of cases is that it's difficult for the model to forecast a situation for which the number of cases decreases suddenly. And I was wondering if it is not due to the thinning operator, in the sense that when you have a large number of cases, the model will predict a low number of cases just after with a quite a low probability. This is due to this thinning operator. So I was wondering if something can be changed.
No, I guess it's not the thinning. I guess the problem is, well, the thinning because it's the responsible for the autoregression thing. The thing is that maybe what should be taken into account is a larger lag for the dependency, so that the autocorrelations do not decay exponentially. I mean, a larger order model. And in that case, maybe things will get better. From the theoretical point of view, it's not so complicated to change the model to have a larger lags. But from computational point of view, is hell. So we have to work on that. So we can have more memory somehow in order to avoid that phenomenon.
Okay, there's another question. Key, you want to ask it?
Yes, thank you very much for your talk. I found it very nice. And I wanted to know, in France, I don't know very much the situation in Spain, but in France, for instance, there has been a very big change since March for the COVID due to mostly the age structure first, and second the testing policy of the government.
Of course.
And I don't know if these are things that you can also add into your model because you had several extension, but is it possible to add, for instance, age structures and also take into account like I forget how to say it in English, but changes, abrupt changes in policies.
Yes, you can put a covariate, and a covariate that is an indicator function, essentially.
Okay.
Theoretically, yes, you can. From the practical point of view, again, estimation becomes complicated. We have to do that, but we need labor force.
Oh, okay.
And more time. We are engaging now into a hybrid way of teaching that will drive us all mad. We are not online, we are part online and part in person, but with half groups. So you don't know who you will be teaching to and what you will be saying to who. If we don't get mad, we will try to yes, not only to add this kind of covariates, numerical covariates, just as temperature and things like that, but also things that, yeah, that change in policies, in testing policies. At the beginning, if we compute things at the beginning and then compute things a little bit afterwards, then you see the changes, the decay in the percentage of underreporting, because, well, eventually a lot of more people got tested, so a lot of more cases were seen and less was underreported.
Okay, I think we have to move on. There was just a last question, but I don't know if you want to answer very quickly. Try to answer very quickly. Paul asked, many people prefer GLM models for this reason, I think.
Sorry?
It
Paul,
was related to the question of Lionel, in fact.
Yeah.
And also for those average change and the
quick
fact that
response
there
if
is more
it's possible.
flexibility.
Well, we tried to use a GAM, generalized additive model, and we got stuck on it. We couldn't make it, but that doesn't mean it can't be done.
Okay, so maybe we're going to move on to the next talk. Viet Ki Tran,